In today's lesson, we're going to learn about multi-threading in C++. So let's suppose we have a situation where we have an intensive computational situation in which there is a lot of processing of large data, and that large data happens to be on the hard drive, and we have to load it in chunks. In that kind of situation, so I'm going to simulate it here in this example to show you how you can actually do that in multitasking so that you improve the performance of your code. So suppose we have a class element which has a buffer pointer. The buffer is basically an array, large array of data that you load, say, from the hard drive of the computer. So that's gonna be a big performance hit due to the slow speed of loading and unloading from the hard drive to the memory. So just to explain what this class is, this is just a simple class, has a constructor which initializes the pointer. Here we're just simulating, it's an example. It basically generates an array of 10 floats on the heap, and then it has an element 1 just for testing that has initialized to 0. This is the default constructor. It has a destructor which basically verifies that the pointer, if the pointer was not deleted, then it deletes the data. So this will get called automatically if you leave the scope from or at the end of program. And then we have just a method here, print, which does print what's in that data for that element class. We then have also a copy constructor. The copy constructor is useful. This basically it's known as the rule of 3 in C++, which means you really have to define how you copy from element to an element. For that reason, I provide the element copy constructor here. This copy constructor basically copies from element E that's passed as a constant and by reference, which means we will not change its value, but we will copy it. So we copy element 1 and we copy the pointer. So the pointer, we need to create first a buffer on the heap of the same size as the element. In our case, we fixed the size to 10. Then we just copy element by element from the source E to the destination this class. What else? That's pretty much it. And actually, I put these in public, so they are accessible if I wanted to, but I could move them down here because it doesn't matter really. I'm then defining using a smart pointer, a shared pointer for a deck. It's a double Q of the class element. The double Q is provided by the standard library of C++. And here we just creating a type so that we don't have to write this whole thing every time we use it. I'm then defining an insert method, which is an external method. So basically I have a main, and main is where everything happens. This is the entry point of the whole program. So we have an insert element, which basically all it does, it takes a smart pointer, a shared pointer, to the deck DQ so that we can modify it by value. That way, when we modify anything inside the insert element, it doesn't get lost. You'll see that here I have basically to push back that element. So here I'm just creating an element and initializing it. Then I'm basically copying it. So all I'm doing is I'm inserting this element into the double queue of element class. So I'm creating a element object of type element class, and then I'm creating a buffer of float of 10 sizes on the heap. Then I'm initializing that with the index of the loop, which means that is going to have 0, 1 to 9, the z. Then I'm just copying the z into the pointer. Actually, I could have just wrote directly the pointer equal to that. There's no point in actually removing this, because this will not get lost. Next, I am just pushing it. And this is actually the place why you have to provide that copy constructor that I explained earlier. If you don't provide that, you won't be able to actually do this. I mean, the behavior will be very strange. It may or may never work. It may throw exceptions, all kinds of hell loose, you'll see, if you don't define the copy constructor here of element. Then, what else? Then I'm creating actually I don't want to talk about that. So now this is what's going to happen. So we want, so this will simulate as if we're actually reading from the hard drive. We're reading the data, this, creating an element class. We then pushing it into a double queue. And the idea is to have the main thread, which is where the main starts, and then spawn a second thread. The second thread will actually keep basically reading from the hard drive and loading data into the deck, into this double queue. And then we can process on that. By processing, I mean just reading the data and popping it out of it. Because this is the idea of actually creating a double deck. I could have just created a queue because I'm not really taking full advantage of deck. Queue would be fine too. And so in this case, we simply just pushing into a double queue the data that is read from the hard drive, and then we're trying to read it at the same time. So it's a good application for improving the performance through multi-threading. So simply here we just create a thread, which we give it the insert loop. It's actually this method, not this one. The insert loop will actually loop over this, and then there is actually a variable from which we can cancel the loop at any moment if we want to exit. If we want the thread to exit, then we have to actually turn this into true. So we're also passing a mutex. The mutex is actually used with the log guard so that the threads, there will never be a race condition. Because every time you access deck queue, the main thread is also, while you're inserting in it, so you're changing the state of it. And depending whether it's empty or not, there could be issues. I mean, I can show once we run it, I can show when we don't use, I will comment out the using of the mutex. The mutex idea is actually to simply lock until this lock is released, meaning that we exited this loop, um, the main thread won't be able to access the deck queue. And the same thing when we also use the on the main thread, when we're accessing the data here, we also putting another log guard on the mutex, so that way, well, every time the main gets access to the double queue, where we actually put the data from the hard drive, we will not, the thread will not be able to access it. So it will have to wait until this guy have left, then it goes and basically does its thing. So let's explain what's in main. So in main, we create a mutex here, a mutex pointer, and we on the heap, we create a deck queue, and we create a cancel variable for a pointer of a Boolean pointer, which we initialize to false. So because we have no false, meaning that when cancel is true, this will exit the loop. So here we dereferencing it, we're just so we're using the also the chrono class. So I have the headers files here. So I'm using, this is IO stream. This is for in and out for using CO, and I'm here defining the standard library namespace, which is used by all of these header files. So once I define here, then I don't need to keep defining each variable that I'm using from this library with its namespace. We have a chrono, we have a thread, and we have the memory. The memory is for smart pointers and for the new keyword and delete. We're using the double queue, and we're using the threads for creating threads. And we're using chrono for basically computing time, the CPU, the system time that I'm using there. So let's go to the main here. In the main, we just like I explained, so we define the cancel variable to false. That means false, not, it becomes true. So this while will keep going. Then I'm at the beginning of this loop, I just get whatever the system clock time right now. Then I compute the difference between, once after you enter, between the current time, every time we get to this level, basically, this start has been initialized to whatever value, then as we loop around, this will keep changing, and we have a positive change until the difference reaching 4 seconds. The cancel will stay false. So once we are past 4 seconds, then this cancel will become true. Then we exit this loop, and also the thread, because it's accessing the cancel variable as well. So it will also, its while loop will also stop. Now, so the idea is very simple. We're just trying to basically simulate the fact that we're creating a thread. The thread has already started reading data now. Here, when we create this thread, we give it the function that it's going to run, and we give it its variables. So I'm giving it pointers. I'm giving it a shared pointer to the deck queue, and I'm giving it a regular raw pointer, cancel Boolean, and I'm giving it the mutex that we're using throughout the whole thing. Then this same mutex is being used with the log guard here, and also in the insertion. So this thread basically keeps looping and reading data from the hard drive and putting it into the deck queue here. And this loop keeps reading. If the deck is not empty, it keeps popping the front, meaning it has done some processing and it's getting rid of it, because we don't want to, as the threads keep running, suppose we have uh, 20 gigabyte of data on the hard drive we're trying to read and process through CUDA or through multi-threading, computing a lot of big matrices or some calculations, lengthy calculation that's based on a lot of frames of data that's stored on the hard drive. So for that reason, we have to pop. We have to do processing somewhere here, then we pop, then we pop the front. So it's a queue. It's a FIFO, first in, first out. So the thread keeps inserting in the back of the queue using the pushback, and this guy keeps popping the front. And once we're past 4 seconds, we're just gonna exit the loop, and also the multi-thread will cancel. The thread will cancel it. My thread will also exit because it's checking on the cancel. We then just compute whatever we're printing, whatever the size of the deck queue after all this processing. We also check, and if it is not empty, then we print whatever data is in it. So let's run it and see what happens. I'm gonna try to do it again, but it keeps running away. I guess what I'm gonna do is put just debug. Okay. It's running, 4 seconds are gone, then it's finished. So we see that it has already checked the size and it found that it is 0, therefore we get nothing. So we don't read here. I'm adding above the return my thread join. This is just so that we have to wait until the thread is dead, otherwise we may run into exceptions. Because if we end the program while the other thread that we created is still running, that's a bad habit. But so now let's modify it a little bit to see that this value becomes something and the print will print something. So let's slow down. Let's slow down this the popping. So we can do that here by making it sleep. So if we make the main thread sleep for a millisecond, we make it 100 milliseconds, then the thread will be able to put much more data than we actually have read or popped out. So let's do that one more time. Why is it being slow? I don't know. Okay. So we can see that now we have a size of 20. That means the thread has read more data than we have processed. That's a good thing. It means that basically by adding a multi-thread, we're able to provide more data than what we can process, which is great. That's what you want. This sleep basically simulates as if we're doing some processing on every single time we read the data. We spend 100 millisecond processing it. Then we throw it away. And that's your data. It shows that basically that everything worked as expected. What else was I gonna show? Yeah, so let me show when you don't do a lock when you don't use mutexes and lock guards on the reading and popping out of the deck, you're gonna run into exception issues. That's because it's like a race condition. So you're gonna run into a race condition over the deck, both the main thread and the other thread that we created and that's running in the background. They're both trying to access the same deck, and that's gonna cause an issue for you. So let's run it and see what happens. All right, run. And bam, look at what happened. So we ran into an exception. So the program has a problem because of that race condition, because we didn't protect the access to the deck, and both the main and they ran for a while, but there was a time somewhere randomly where they crossed path, where the main thread and the background thread, they both tried to access the deck, and basically a race condition happened. So if we do a retry, then we can break. We can check the call stack. If we check the call stack here, we can go back and see where it actually happened. So somewhere, you see somewhere there was a call for destroy, and then due to the pop front. So if we go inside main, that's where it happened. So if we check it was here, this is the call stack. After we actually called this, there is a chain of processing. When you do a pop front, basically there will be a destruction of that element class, and the destructor of this class will get called. When that happened, apparently we're already trying to access the same thing, and that's not allowed. And so this is basically what's going to happen if you don't protect your code with lock guards. So if we put the lock guards back, then we should run fine, and we can do multi-threading safely, and that's basically safe multi-threading for you in C++. And this is what was printed. It's printed after every insertion. We're just printing this message to the console through cout. That's it. Thank you very much. I hope it was very clear for you.